Hello students, welcome to the class of Real Analysis. We are following the textbook Principles of Mathematical Analysis, 3rd edition, Walter Rudin. Metric spaces. So in order to define metric spaces, first of all we need to define what is a metric. So generally, what is a distance? Distance is a function, right? What is distance? Distance can be defined when you have points on a some set. So suppose there are suppose capital X is a set, okay, then distance between two points X and Y in capital X is defined by a function. So distance is always a function from capital X cross X to R plus union set 0. So distance is always a function from cross product of the set into R plus union set 0. Okay, so we will represent this distance as some D. Then distance D is a mapping from X cross X to R plus union set 0. Okay, then what are the important properties of distance? We all know distance is always positive. So D is always, I will denote D. Elements of X cross X are ordered pairs, so we can define D of XY, okay. Then D of XY should be always positive for any points X comma Y in the given set capital X. Distance is always positive, that is the first point. Second point, when you calculate the distance between before that, whenever the distance is equal to 0, when you calculate the distance is equal to 0, then we know that they are same points, right? When the distance between two points are 0, which is only happen when X is equal to Y. Okay, and reverse also, when X equal to Y, distance between that two points are 0. So the second property is distance from any two points, between any two points is equal to 0 if and only if that 2 points are same or equal. And the third point, the distance from X to Y should be equal to distance from Y to X. Okay, and the fourth point, triangle inequality. We say that it is triangle inequality. That means when you have 3 points X, Y and Z, then you calculate the distance between X and Y, and you calculate the distance between Y and Z, then you calculate the distance between X and Z, okay. So this distance is D of XZ, and this distance is D of YZ, and this is some D of XY. Then D of XZ should be less than or equal to D of XY plus D of YZ. Okay, if it is true for every points X, Y, Z in the capital X. And this property is actually called a triangle inequality. Triangle inequality. Triangle inequality. Okay. So distance have all these 4 properties. Now we generalize this concept of distance. So distance will not be same as always the straight line distance. Okay, which is called the straight line distance. Actually, we all know that when you have 2 points in real line, suppose we have a real line, okay, then if you have X and Y in real line, then what is the distance between X and Y? Between X and Y, that will be either Y minus X or X minus Y, right? According as X is less than Y or Y is less than X. And when you have 2 points in the plane, when you have X and Y 2 points in the plane, then X will be equal to X1, X2, Y1 will be equal to Y1, Y2 because they are belongs to the plane. Then what is the distance between X and Y? So that is actually denoted by modulus of X minus Y, which is nothing but the Euclidean distance, right? Root of X1 or Y1 minus X1 the whole square plus Y2 minus X2 the whole square. Okay, so these are the usual distances in R, R2 and R3 etc. Okay, so distance in different sets will be different. So we generalize this concept of distance. That is actually called a metric. So what is a metric? Metric always has all these properties of distance. So what is a metric? A metric D on a set X. So when you have a set capital X, we can define metric D, which is represented by D on X. Okay. And what is metric D? Which is always a function from word to word, the same domain to same range, that is X cross X2 R plus union set 0. So because the distance cannot be negative, so we exclude the negative real axis, and distance is always a real number. Okay, so that's why our metric is a function from X cross X to R plus union set 0. Okay, and when we say this function is a metric, if it satisfies all these properties of distance. So a metric D on a set X is a function from X cross X to R plus union set 0, and it satisfies all those properties of distance. The first one is positive definiteness, D of xy is greater than or equal to 0. And second one, D of xy is equal to 0 if and only if x equal to y. And third one, D of xy should be equal to D of yx, that is called as symmetry. And fourth one, triangle inequality, D of xz should be less than or equal to D of xy plus D of yz. And these all should be true for every element xyz belongs to whole space X. Okay, so metric is always a function. Metric is always a function. Right? Then when we have the set capital X and the metric D, then the pair XD is called a metric space. Pair XD is called a metric space. So what is a metric space? Metric space is a set together with a metric. A non-empty set together with a metric D is called a metric space. Okay. Okay. Now we will see what are the examples of metric spaces. Okay. For example, consider the set X is equal to real line. Our real line. Okay. Now define D is a metric from R cross R, X cross X, here is R cross R, to R plus union set 0. Okay. Defined by D of xy is equal to, we know that the distance between two real numbers is always modulus either x minus y or y minus x. So we can write it as modulus of x minus y. We take the positive thing only. D of xy is equal to modulus of x minus y. Okay, then we can prove that this modulus or the usual distance in the real line is an example of a metric in real line, because it satisfies all the properties of metric. Okay, let's see what are the properties. We have to prove that D of xy should be greater than or equal to 0 for every element xy, right? So consider D of xy for elements x and y. So by definition it is modulus of x minus y. We know that modulus of a number is always positive. Modulus of a number is always positive, so it satisfies the first condition. And second condition, assume that D of xy is equal to 0. If D of xy equal to 0, then by definition modulus of x minus y equal to 0. And we know that modulus of a number is equal to 0. Okay, let's continue. So modulus of x minus y equal to 0 means we know that which is only happen when x minus y equal to 0. Modulus of a number equal to 0 if and only if that number is equal to 0, because it can't be negative. So it will be 0 only when that number is equal to 0. Okay, which is if and only if x is equal to y. So we proved that when D of xy is equal to 0, if and only if x equal to y. Okay. Now the third one, you consider D of xy. We need to prove that there is a symmetry. That means that is D from x to y will be equal to D from y to x. So D of xy equal to, we know that it is x minus y. It is given. So that is can be written minus of y minus x. And we know that modulus of a negative number is equal to modulus of the same positive number. So that is y minus x. And which is can be written D of yx. So D of xy will be equal to D of yx. So there is a symmetry. And fourth one, triangle inequality. So for consider D of xz. By definition it is modulus of x minus z. Okay. Then we add and subtract the term minus y plus y inside that modulus. So that can be written x minus y plus y minus z. And you take these as this x minus y as a number a and y minus z as number b. Then we know that modulus of a plus b is less than or equal to mod a plus mod b. So that will be mod x minus y plus mod y minus z. And what is modulus of x minus y? Which is nothing but d of xy. And what is modulus of y minus z? It is nothing but distance between the y and z, or the d of yz, metric dyz. Okay, so we proved that dxz should be less than or equal to d of xy plus d of yz. So we prove we proved all the properties of metric which is satisfied by our usual modulus in real numbers. So which implies the function modulus, the distance modulus is a metric. Modulus is it is a metric on set of real numbers. So real line with this metric is a metric space. And this metric is called actually usual metric on R or standard metric. This metric is also called usual metric or standard metric because it is always used to find out the distance between real numbers. Actually it is a straight line distance from x to y. Okay, so real line with the modulus is called the usual space or standard space. That metric is called usual metric or standard metric. Okay. Another example, take x is equal to R2 the plane. Okay, and define a metric D from R2 cross R2 to R plus union set 0. Okay, which is defined by D of xy is equal to modulus of x minus y. What is this actually? So here the modulus means the Euclidean distance. Here x and y belongs to R2 means they are ordered pairs. So x will be equal to some x1, x2 and y will be equal to some y1, y2, right? Okay. Then distance between x and y, modulus of x minus y is actually the Euclidean distance, which is nothing but y1 minus x1 square whole square plus y2 minus x2 the whole square. That means the difference between first coordinate and the difference between second coordinate, their square and sum. Okay, raised to 1 by 2. So this is here modulus now, and we can prove that this metric this modulus also an example of metric in R2. And in a similar manner of the proof of real line with the usual metric, we can prove that R2 with this metric is also metric space, is a metric space. Now next example, again we consider x is equal to R2, okay, and I will define D of xy is equal to maximum of modulus of x1 minus y1 comma x2 minus y2, where x is equal to the pair x1 x2 and y equal to the pair y1 by 2. Okay, so note that this d of xy is not equal to the usual distance modulus of x minus y. Here we taken the difference between first coordinate and difference between the second coordinate and their maximum value. And I am going to prove that this function is also a metric in R2, another metric in R2. Okay, so I have to verify all the properties of D, and you can see that D is clearly a mapping from x cross x. That means here R2 cross R2 is clearly mapping from R2 cross R2 to, and you can see that modulus of a number is always positive. Okay, so these two numbers are always positive, their maximum will be always positive. Okay, and when x and y are two ordered pair of real numbers, their difference, first coordinate differences will be real number, second coordinate differences will be a real number, their modulus value always a real number, and their maximum is always a real number, and they are always positive including the element 0. So the range should be R plus union set 0. Okay, now we will verify the properties. First one, consider d of xy. What is d of xy? By definition, maximum of modulus of x1 minus y1 comma x2 minus y2. Okay, since modulus of a number is always positive, modulus of x1 minus y1 is positive and modulus of x2 minus y2 is always positive, therefore their maximum is maximum of modulus x1 minus y1 comma x2 minus y2 is positive, implies d of xy should be positive for every x equal to x1 x2, y equal to y1 y2 belongs to R2. Okay, now the second property, d of xy, assume that d of xy equal to 0. So when d of xy equal to 0, maximum of modulus of x1 minus y1, comma x2 minus y2 is equal to 0. Okay, maximum of two positive elements are equal to 0. Maximum of two positive real numbers are equal to 0 if and only if both the terms x1 minus y1 equal to 0 and modulus of x2 minus y2 equal to 0. So which is if and only if x1 minus y1 equal to 0 and x2 minus y2 equal to 0. Which is if and only if x1 equal to y1 and x2 equal to y2. So when x1 equal to y1 and x2 equal to y2, the pair x1 x2 will be equal to y1 y2, and which means that actually if and only if x is equal to y. Okay, so d of xy equal to 0 if and only if x equal to y will happen. Now for the third property, symmetry, consider d of xy. So by definition it is maximum of modulus of x1 minus y1 comma x2 minus y2. So this can be written maximum of modulus of y1 minus x1 comma y2 minus x2. So this is by definition d of first coordinates, that is y1 y2 comma x1 x2. What is y1 y2? Y. What is x1 x2? X. So we get d of xy will be equal to d of x for every xy in R2. So symmetry will be true. Now the last part, triangle inequality. So for that we consider d of xz. D of xz will be maximum of x1 minus z1 comma x2 minus z2. Okay, so now consider the first term x1 minus z1, modulus of. Consider modulus of x1 minus z1. So we add and subtract the term y1. So x1 minus y1 plus y1 minus z1. So we know that modulus of a plus b less than or equal to mod a plus mod b. So this is x1 minus y1 is the term a and y1 minus z1 is the term b. Okay, so this will be less than or equal to modulus of x1 y1 plus modulus of y1 minus z1. Now this will be less than or equal to, what is x1 minus modulus of x1 minus y1? Modulus of x1 minus y1 is always less than or equal to maximum of modulus of x1 minus y1 comma x2 minus y2. The first term will be less than or equal to maximum of these two terms. So maximum of these two terms is always greater than or equal to the first term and the second term. Okay, because it is a finite set. Similarly, modulus of y1 minus z1 is always less than or equal to maximum of the term including y1 minus z1 comma y2 minus z2. Okay, we replace each term by its maximum. Maximum of a set including that term. Okay, so what is this first term? Maximum of these two terms is actually distance between x and y, plus maximum of these two terms is distance between y and z. So we proved that the first term of d of xz is less than or equal to this distance. Now consider the second term. Consider the second term, modulus of x2 minus z2. Here we add and subtract the term y2, x2 minus y2 plus y2 minus z2. So this will be less than or equal to this by similar argument, x2 minus z2, x2 minus y2 plus y2 minus z2. Now we replace each term by its maximum. So this will be less than or equal to maximum of the term x2 minus y2 comma x1 minus y1. Okay, plus, and we replace modulus of y2 minus z2 by its maximum of modulus of y2 minus z2 comma y1 minus z1. Okay, so what is this first term? That is nothing but d of xy. Second term, d of yz. So we proved that each term modulus of x1 minus z1 less than or equal to this sum and modulus of x2 minus z2 less than or equal to this sum. So when both the terms satisfies or both the term have some upper bound, its maximum also has the upper bound, same upper bound. Therefore I can write maximum of modulus of x1 minus z1 comma x2 minus z2 will be less than or equal to d of xy plus d of yz. And what is this by definition? D of xz. So we proved that d of xz is less than or equal to d of xy plus d of yz. So what we can say is R2 with this metric is a metric space. And this metric has has a name which is called maximum norm, maximum metric or submetric. This metric D is actually called submetric because it is suprema matrix or maximum metric, submetric. And it is denoted by, D infinity. D suffix infinity.